Hi, I'm Ken Black. Welcome to Business Statistics for Contemporary Decision Making. Today we're going to learn about type 1 errors and we're going to learn about type 2 errors. In statistical hypothesis testing, once we make a decision, we've either made a correct decision or we've made an error. In statistical hypothesis testing, there are two kinds of errors. There is the type 1 error and the type 2 error. Let's talk about the type 1 error first, what it is, and how it can be committed. A type 1 error is committed in statistics when we make the decision to reject a null hypothesis, but the null hypothesis turns out to be true. That is, we have actually made the decision to reject a true null hypothesis. Type 1 error has a couple of other names that we often refer to it. Type 1 error is often measured in something called alpha, and sometimes the type 1 error is called the level of significance, which sometimes is given as a percentage. What are some common values of alpha? If you're a student working a problem, it's most likely that the value of alpha or the level of significance is given to you in the problem. For business statisticians working in the field, however, there are a few common values of alpha that they use. Perhaps the most common value of alpha is 0.05. And sometimes we use an alpha value of 0.01 if we want to protect more against committing a type 1 error. On the other hand, the highest value of alpha that you generally see in statistical analysis is 0.10. It protects less against a type 1 error. There are some examples of how type 1 errors can be committed in our everyday life. For example, in a court of law, convicting an innocent person is in effect committing a type 1 error. Let's take a look at the notion of type 1 error in our bottling example. Let's go back. Suppose that we're testing that the population mean is 20 ounces. Knowing that sample means are normally distributed, we establish a critical value. Suppose our critical value is 19.6 ounces. We have determined ahead of time if our sample mean is less than 19.6 ounces, we are going to reject a null hypothesis. Suppose we go out and we sample our bottles and we get a sample mean of 19.5 ounces. Based on our decision rules that we made ahead of time, our decision will be reject the null hypothesis. Once we decide to reject the null hypothesis, we've either made a correct decision or we've committed a type 1 error. Let's think about how a type 1 error could have occurred in this instance. Well, suppose our alpha value for this particular problem was 0.05. What that means is we have established ahead of time that 5% of our area is in the rejection region. We know that the sample means will be normally distributed, and they're going to be above and below possibly the population mean. And when we set this critical value there, we're taking a 5% chance that when we get a value down here, it just happened by chance that the population mean is actually 20 ounces, and that, for example, our 19.5 was just a random draw of bottles that happened to fall down here. So our dilemma is, did our result of our sample that's caused us to reject the null hypothesis, is it just a chance result that fell in this tail, or does it indicate that something else is happening? Since the value of alpha in this particular problem is 0.05, and we have a 5% chance of doing the wrong thing, you might think, well, why don't we just let alpha be 0.00 and not have any probability of type 1 error? Well, the problem is there is a type 2 error that goes in opposition to type 1 error. So now let's talk about type 2 errors. A type 2 error, on the other hand, is when you fail to reject a false null hypothesis. An example in the court of law system would be when you fail to convict a person who is guilty of a crime. Type 2 error is denoted by beta, this Greek letter, and beta is the probability of committing a type 2 error. let's take another look at our bottling problem and see how we could possibly commit a type 2 error. If you'll remember, the null hypothesis in our bottling problem was that the bottles were averaging 20 ounces, that we had a critical value at 19.6, after which you have a rejection region. Our alpha was 0.05. Suppose we sample 50 bottles and our sample mean is 19.8. Then we decide, since our sample mean lies in our failed to reject region, that we will make the decision not to reject the null hypothesis. Suppose, on the other hand, though, that the company is actually averaging 19.7 ounces. And we'll call this the alternative population mean, 19.7 ounces. Then, by making the decision to fail to reject the null hypothesis with this sample value, we have committed a type 2 error because the company is actually averaging 19.7 ounces in their bottle fills. If we were to take this critical value and dash it on down into the second distribution and hatch this part of the distribution in, we would discover that all this part of the distribution is part of beta, or the probability that we are committing a type 2 error. So what happens is, in this alternative distribution, where we're not filling the bottles with 20 ounces anymore, this part of this distribution is so close to the 20-ounce distribution, it looks like that the company is actually filling 20 ounces. And so, in effect, we get fooled with these. And so we will find sample means in this part of the distribution here. Our decision will be to fail to reject the null hypothesis, and we'll commit a type 2 error. As another example, suppose the company is not averaging 20 ounces, but they are actually averaging 19.4 ounces. Now, what would be the probability of committing a type 2 error? Well, again, we take our critical value from the assumed null hypothesis distribution. We dash it down into the second distribution, which is going on. We don't know about it. And when we hatch in this part back over here, this is our beta error, or our probability of type 2 error. Notice that beta is smaller in this particular problem because the alternative mean that may be occurring is further away from our null hypothesized mean. While in any statistical hypothesis test, there is only one value of alpha, there can be a number of possibilities for beta depending on what's happening with the alternative hypothesis. So how do type 1 errors and type 2 errors relate? That is, how do we relate alpha and beta? Well, alpha is the amount that we put in the rejection region, and it's the probability of a type 1 error. But the probability of type 2 error, or beta, is on the right side of the critical value in this particular drawing. You might be able to see that if we decide to reduce alpha by extending our critical value, then what will happen as this line moves this way to the left, beta will increase. That is, alpha and beta are inversely related. If we decide to reduce beta such that this line comes back to the right, then the value of alpha will increase. So alpha and beta are inversely related. So it appears that if you decide to reduce one error, that will cause an increase in the other error. However, there is a way to reduce both errors, and that is to increase sample size. So by taking larger sample sizes, we can actually reduce the probability of a type 1 error and a probability of a type 2 error at the same time, all things being constant. So to summarize, research hypotheses are tested by formulating them into statistical hypotheses. And statistical hypotheses have a null hypothesis and an alternative hypothesis. In testing statistical hypotheses, we always assume that the null is true at the beginning of the test. As common convention, we always write the null hypothesis with an equal sign in it. When we set up our hypotheses and we go to make a statistical test, we have a dividing number between the rejection region and the failed to reject region, and it is called the critical value. Type 1 error is an error committed by falsely rejecting a true null hypothesis, and alpha is the probability of committing a type 1 error. The probability of committing a type 2 error is beta, and a type 2 error is failing to reject a false null hypothesis. Also, alpha and beta are inversely related. If you reduce alpha, you're likely to increase beta, and vice versa. The only way to reduce both of them at the same time, all other things being constant, is to increase the size of the sample size, or n.